Hello everyone, it's a great honor to present our research at the 2024 ACM-BCB conference. Today, I will introduce our study titled Causality-based subject and task fingerprints using fMRI time series data. This research represents a team effort between group from George Mason University, the University of Pennsylvania, and the United States Naval Academy. The team members involved in this project include myself, Dachuan Song, along with Dr. Li Shen, Dr. Dui Dongchuan, and Dr. Xuan Wang. In this presentation, I will give you an overview of the main content. First, we will start with the introduction and the motivation behind our research, followed by the key challenges we faced. Then, I will explain our proposed two-timescale state space model in detail and show its application in both subject and task fingerprinting. After that, we will present the experiment results to confirm the effectiveness of our approach. Finally, we will conclude with our main findings and discuss possible directions for future research. Next, I will guide you through the motivation of our study. In neuroscience, with advance in image technology, we can now observe human brain activity through fMRI by detecting change in blood flow. fMRI indirectly reflects brain activity, particularly through the Bordeaux effect, which stands for blood oxygen level dependent. Given the nature of fMRI data, we believe it has a potential to provide detailed insights into brain function. However, current methods do not produce good enough results in analyzing this data. Therefore, we aim to use an innovative model to process the data, allowing us to achieve more accuracy identification. With the vast account of MRI data we have, but a lack of effectiveness tool to analyze it, we are left a key question. Can causality be utilized as a definitive signature of brain activity for performing subject and task fingerprinting? Our goal is to capture the directional interactions and dynamic features between brain regions. However, current methods are limited in this regard, as they lack comprehensive causality analysis capabilities, which reduce the effectiveness of data analysis results. In addition to fMRI potential for understanding brain function, survival challenges remain. There is high variability and limited data, which makes the generalizations difficult. Brain activity patterns are complex and hard to interpret, and capturing directional and temporal dynamics is challenging. To tackle this problem, we reviewed many existing methods to find the most suitable model. The most widely used method is functional connectivity, or FC, which identifies connection patterns by calculating correlations between brain regions. While this approach has a low data needs and is helpful initial functional analysis, it can't capture directional interactions or dynamics changes between regions, which limited its ability to analyze the full range of data features. Another method is independent component analysis, or ICA, which extracts independent spatial component from the data, indirectly capturing some dynamic information. However, ICA requires a lot of data and can't directly show directional interactions between regions. Compared to other methods, we choose a causality-based approach, where it's not entirely new. It has been fully explored in this context. We believe it holds a strong potential for fMRI causal fingerprinting. Causal analysis not only captures correlations between regions, but also identifies the directions of interactions and temporal dynamics. With this advantage, we see causal analysis as well suited for subject and task fingerprinting in fMRI data. Moving on to our dataset, we used a refined selection from the HPCYA fMRI data. focusing on the 391 unrelated individuals. This includes resting state data and 7 distinct text-based conditions, such as emotion, gambling, language, motor, relational, social, and working memory. We process the data using Schiffer parcellation with a resolution of 100 pixels. It includes multiple task types, providing strong support for causal fingerprinting across different subjects and tasks. In this section, I will explain our approach to obtain causal fingerprints for subjects and tasks. We define a causal fingerprint as a unique cause and effect cognitive signature that distinguish a subject or tasks in an fMRI data. First, we develop a novel two-timescale state space model using generalized least square for accuracy parameter estimation. This model captures both fast and slow dynamics interactions with the brain. Next, we applied this model to accurately identify the causal fingerprints of individual subjects, demonstrating its effectiveness in distinguish unique brain active patterns. We then extended this approach to task-based identification, allowing for precise recognition of task brain dynamics. Now, let's look at the model we developed. To extract causal fingerprints, we developed a two-timescale state space model that captures causal dynamics. This directly time linear state space model enables us to track both fast and slow dynamics change in brain activity. The model curve formula is x of t equals q times x of t plus a times x of t minus 1 plus b times u of t minus 1. X of t represents the system state as the current time t. Matrix Q represents the rapid dynamics, showing how the system state interaction concurrently within the same time step. Next, we have x of t minus 1, which is the system state from the previous time step. The matrix A captures slow timescales dynamics, showing how the previous state influences the current state, allowing us to model long-term changes over time. Then, U of t minus 1 represents the input at the previous time step. The matrix B describes how some key regions influence the current state of the system. By combining these elements, our model effectively captures both rapid short-term interactions and slower long-term changes in brain dynamics, providing a comprehensive understanding of the causal relationships. The input matrix B reflects how some key regions impact the system state. To define these input nodes effectively, we choose 10 input nodes from a total of 100 brain regions, focusing on functional important areas like the premotor and the sensor cortices that are related to task execution. The other 90 nodes are used as system state nodes. To calculate and obtain matrix Q, A, and B in our model, we use a data-driven parameter reconstruction approach. Specifically, we estimated this matrix through a generalized least square problems by throwing in the object function. Our goal is to minimize the difference between the predict value and the observed values. The predict value refers to the system state x of t that our model estimated based on the matrix A, B, and Q, as well as the previous state and the inputs. The observed value are the actual system state x of t, obtained directly from the fMRI data. The constraint that the diagonal elements of Q are zero ensures that there is no self-feedback within faster dynamics. This approach allows us to optimally infer values for A, B, and Q, achieving accuracy reconstruction of the system parameters. Next, I will walk you through the workflow of a causal dynamics model. We start by collecting real-time series data, capturing brain activity using Schiffer parcellation, as shown in Figure A. Once we have this time series data, we apply our causal dynamics model in a data-driven manner to uncover how different brain regions interact over time. This model allows us to construct an internal interaction map within the brain, focusing on the both fast and slow dynamics. Through this process, we generate the key matrix Q, A, and B, which you can see in Figure B. By extracting these dynamic features, we gain deeper insights into the brain functional architecture and its response to different cognitive tasks. After processing the model, we use dynamic model decomposition and projection to achieve subject identification. Let's walk through how it works. First, we decompose the dynamics of the labeled data in our database. For each sample, we separate the fast and slow dynamics component. Specifically, fast dynamics are represented by QD, while slow dynamics are represented by AD. This decomposition allows us to capture two timescales of the brain activity pattern in the labeled data. Next, we apply the same process to the query data. For query data with unknown identity, we extract its fast dynamic, noted as QQ, and its slow dynamics as AQ. By treating the query data in the same way as the label data, we obtain a comparable dynamics representation. Then, to identify the subject, we propose the optimizing matching. We aim to matching the query data dynamics model with the labeled subjects. This is done by minimizing the distance between projection matrix of the query data hat T Q and the labeled subject bar T using the following formula. The distance is calculated using the Euclidean to see how closely query data aligns with its labeled subject. By identifying the subject that yields the smallest distance, we can accurately determine which subject the query data most closely matches based on its unique dynamics patterns. This method allows us to capture both faster and slow brain dynamics, enabling precise subject identification using their causal fingerprints. Next, let's look at the result of subject fingerprint experiments. In the bar chart on the left, we show the accuracy of our method for subject fingerprinting. Each color bar represents a different rest session and scan order. Let's focus on the first part. The orange bar represents rest 2 IR. The yellow bar represents rest 1 RL. And the purple bar represents rest 2 RL. This reset of data were matched against rest 1 LR to obtain results shown. The same process was applied for the remaining three comparisons. The black line in each bar indicates the performance of the baseline method using functional connectivity with correlation. It's clear that our result outperforms the FC and the correlation method. We designed these comparisons to evaluate whether incorporating causal dynamics could significantly enhance identification accuracy. Now let's focus on the table below. Here we present a detailed comparison of multiple methods, including our proposed causal dynamics model with the modeling decomposition and the projection, functional connectivity, combined with the various other techniques and the graph neural network. The different methods in the table were chosen to assess how various modeling techniques, including traditional and deep learning approaches, performing under the same conditions. The causal modeling and projection approach achieves the highest accuracy, reaching over 81% in some cases. This shows the effectiveness of using causal fingerprints to identify subjects, even in challenge resident state conditions. In construct, the correlation and Frobenius normal methods did not perform as well, with accuracies generally below 50%. Interestingly, while FC and projection showed improvement over FC and correlation, it still did not reach an accuracy level achieved by our causal dynamics approach. Regarding the GNN method, we found that it was not suitable for subject fingerprinting due to data limitation. We also explored other deep learning methods using convolution or attention-based layers, but they showed similar poor performance, often below 5%. The key takeaway here is that our causal modeling and the project method consistently outperforms traditional correlation-based method, demonstrating the potential of the using causal dynamics for more accuracy subject identification. In the second task, we focused on task fingerprinting using a graph neural network, or GNN, to achieve task recognition. Here are the key details of our data construction, model structure, and the training process. First, we build on graph structure based on the matrix Q, A, and B from our causal dynamics model. This matrix captures the causal relationships between different brain regions. Each node in the graph represents a brain region, effectively translating the dynamic features of task into graph input. Our GNN model is built with a 5-layer structure, as shown in the figure. To train the model, we mix the processed data from both the LR and the RL scan, and then randomly split the data using 50% for training and 50% for testing. Additionally, during training, we set the following main parameters. The combination of our data processing, model structure, and training strategy ensures effective task causal fingerprinting, allow us to capture distinct task-specific patterns in brain activity. After training the GNN, we presented the task fingerprint results using a bar chart. Each color represents a special task, as shown in the figure. It's clear that our model achieves a perfect accuracy of 100% for the resting state. For tasks like emotion, language, and working memory, the accuracy is also impressive high. However, for tasks such as gambling, motor, relational, and social, the accuracy is lower, with most of the misclassifications occurring internally among these tasks. Next, let's take a close look at the comparison results. Following the previous results, let's now move on the table comparison of method with state-of-the-art techniques. To demonstrate the advantage of our proposed causal modeling and GNN method, we constructed experiments across 8 tasks, comparing it with multiple baseline methods. In our experiments, we use our causal modeling as a feature extraction method, directly comparing it with the functional connectivity approach. After extracting feature, we applied various classifiers, including GNN, random forest, spot vector machines, as well as deep learning methods like DN, DBRN, and brain attention network decoding. These classifiers were chosen because they represent either commonly used or top-performing techniques in brain activity patterns analysis. The result, as shown in the table, clearly highlights that the causal modeling and the GNN method achieves the highest accuracy, with an average accuracy of over 98% across all tasks. This demonstrates the effectiveness of the using causal fingerprints combined with a graph neural network for task identification. However, we did notice a slightly drop in accuracy for tasks like gambling and motor. This is likely because this task has more overlapping neural active patterns, making them hard to distinguish. It's worth mentioning that other methods, such as RODIT and GNN, and RODIT and DBRN, also showed reduced performance in these challenge tasks. We also compared our method with the brain attention network decoding approach, which use volumetric data in an end-to-end deep learning framework. Even though volumetric data generally offers higher resolution than the Schaefer 100 tessellations used in our work. Our causal modeling method still achieved comparable and in some cases slightly better accuracy. Our method works very well in task fingerprinting. This shows the potential of our approach for wide use in brain activity analysis. Our approach visualizes the impact of different tasks on brain regions. The figure shows the brain regions with the strongest connection weight in each task through matrix Q and A. Arrows indicate the directional influence between regions, illustrating which areas have significant causal effects on others across different tasks. These visualizations provide clearly support for further analysis of brain activity patterns. Next, let's take a closer look at the characteristics of the working memory tasks. In the working memory task, we observe strong influence processes in specific brain regions. The figure shows the strong connection with linked to the working memory tasks, visualizing causal interactions between brain regions through matrix Q and A. We see that the parietal cortex play a key role in processing sensory information, while the dorsolateral prefrontal cortex, or DLPFC, serves an important function in cognitive tasks. These two regions form the main causal interaction in the working memory tasks, while DLPFC activities affects parietal cortex response through causal pathways, further enhancing sensory information processing and task completion. Our model offers evidence for understanding how cognitive processes working in the brain. In summary, our goal was to leverage causal fingerprinting to enhance our understanding of our brain activity patterns by capturing the directional interactions and the dynamics of our brain regions. We aim to accurately identify subjects and tasks based on their unique brain signatures. Now, let me highlight what we were able to accomplish with this approach. First, we developed a novel two-timescale state space model for causal fingerprinting, which offers a new perspective for identifying both subjects and tasks. Second, we successfully applied causal fingerprinting to distinguish subject and task finger patterns. Lastly, we validated the model's reliability, achieving high accuracy in recognizing both subject and tasks. Overall, this approach provides a robust framework for using causal analysis to gain deeper insights into brain function, offer a promising approach for future study in neuroscience. Some limitations remain, such as relying on predefined system inputs and limited generalization in task fingerprinting. These challenges create opportunities for future research. Moving forward, we plan to test different system inputs to enhance the model ability. We also aim to use high-resolution brain maps to capture more detailed brain activity. Additionally, we will focus on the making model perform well across different tasks and datasets. Finally, we plan to apply this method to clinical data like Alzheimer's research to help with diagnosis and treatment. Thanks you all for your attention. I would like to express my thanks to my cooperators for their valuable contributions to this project. Unfortunately, due to some circumstances, we are unable to attend this conference in person, so we won't have a live QA session today. However, we have provided the email of each author here. If you have any questions or would like to discuss our research further, please feel free to reach out to us by email. We truly appreciate your interest in our work. We hope that our research offers a fresh perspective on using causal fingerprinting in neuroscience